Hello, I am Seema and welcome to part 25 of the chapter Organic Chemistry, Some Basic Principles and Techniques. In this video, we are going to talk about resonance structures. In part 7 of this chapter, I told you about Kekulé's dream. When he was imagining the structure of benzene, he knew that there are 6 carbons and there are 6 hydrogens and all the valencies are being satisfied. But he could not imagine of a structure where all the valencies would be satisfied if we had an open chain structure. So one day when he dreamed that a snake put its tail in its mouth, he suddenly got up, woke up from the dream and he started making the structure of benzene, joining the 6th and the 1st carbon atoms and thus leading to a ringed structure. And then he imagined that there are 3 double bonds and these double and single bonds are alternate double and single bonds. So he made this structure where there were alternate double bonds, and now he found that every carbon was forming 4 bonds and every hydrogen was forming 1 bond, and the properties of benzene could really be explained on the basis of such a structure. Now take a look here. If this is every corner is a carbon, this carbon is attached to the adjacent carbon by 2 bonds and it is attached to this carbon by a single bond. So the total number of bonds with other carbons is 3 and 1 hydrogen. So every carbon is forming 4 bonds and every hydrogen which is present at every corner of the hexagon, it has 1 bond. The carbon hydrogen single bond. So every carbon forms 4 bonds and every hydrogen forms single bonds. So this structure theoretically was a very good structure. But now as time passed, there were a few problems that started creeping up, Benzene, when you looked at it under a microscope or a very strong microscope, or you tried to analyze its reactions, that if this is a single bond, the bond length between a carbon-carbon single bond should be 154 picometers. And the bond length between a carbon-carbon double bond should be carbon, double bond carbon should be 134 picometers. Then the behavior of these bonds should be different. A double bond in benzene should behave differently from a single bond in benzene. And its lengths, the lengths of the double and the single bonds should be different. But it was found that all the bonds, they have an equal length. All of them are neither 154 nor 134, they are somewhere in between these two. And that value is 139 picometers. The actual bond length in benzene is 139 picometers and all the bond lengths between each carbon are equal. It is as if in benzene, the carbons are behaving in a way that they do not know whether they are singly bound or are they doubly bound. Right? Now there were 2 structures that could have represented the same structure as Kekulé had explained. Take a look here. Here, if this is the first structure and this is the second structure. In the first structure, this is carbon 1, 2, 3, 4, 5, 6. Similarly, in this also, this is carbon 1, we'll number it in the same way. In the first structure, the double bonds are between carbon 2 and 3, 4 and 5, and 6 and 1. Right? Because this is carbon 1. In the second structure, the double bonds are between 1 and 2, 3 and 4, 5 and 6. So the position of the double bonds is different. And yet, when you look at benzene and the behavior of all the bonds, all of them behave equally and they neither behave like single bonds nor like double bonds, which gives us a feeling that these structures are not actually right. They are right theoretically that they should be, because each carbon is getting its 4 bonds, each hydrogen is getting its bond, yet there is something wrong in these structures. And how would you explain this one with this one? They are both different if you really look at them, yet they are both correct. So the concept came in that let us imagine that these second bonds are not fixed between the atoms. Let us say this is also right and this is also right. And this is kind of partially right and this is partially right. So we take both the benzenes and we overlap them with each other. Keep one benzene molecule and put the second benzene molecule over this. If I place this benzene molecule over the first one, what will happen? The double bonds here, you will start seeing of this benzene, the double bond, you will see it here, you will see it here, and you will see it here. So you will start seeing a ring within benzene. and the double bond of the two kind of are making a complete circle. And if this is uncertain, let us make this one uncertain too. That this bond is not definitely here, because this is also partially right and that is also partially right. Then you get this electron displaced model, where the pi electrons, they are displaced. Such a structure is actually a resonance hybrid. We say both the structures are resonating, both of them are present together, and this is the final structure that you are getting. Such a structure is known as a resonance hybrid structure or a resonance structure. Let me just go back to this. So initially, we had benzene with solid bonds like this, these two structures. And as a result of this, you will get a hybrid. And the hybrid or the actual molecule is such that although due to dearth of space, my benzene ring is not very proportionate, but all bonds are of equal length and the electrons are shown by a dotted circle. That they are equally, the pi electrons are kind of equally distributed between all the bonds. And therefore, all these bonds are neither absolutely single bonds nor are they absolutely double bonds. They are somewhere in between. And if they are somewhere in between, then this bond length makes sense. That yes, a bond length which is neither a double bond length as short as a double bond nor as long as a single bond, the bond length, all bond lengths are equal and they are 139 picometers. This is the concept of resonance. That when you have a certain compound whose structure cannot be shown by a single structure, you need different structures, and these different structures are hypothetical, they are imaginary. The actual structure cannot be explained by any one of them. The actual structure of the molecule is a hybrid of them. It is a resonance hybrid. And this delocalization of electrons is known as resonance. It is resonating, like sound resonates. If there's a nice song that you listen to, it keeps resonating in your ears. So comes and goes, comes and goes. So it is somewhat like that. The double bond and the single bond are kind of resonating. They are vibrating between the different bonds. So the behavior of many organic molecules cannot be explained by a single structure. In those cases, we find that the resultant molecule is actually a result of the mixture of those individual structures. So according to these structures, you would have, which are known as the resonance structures. These are the individual canonical forms or the resonance structures. And the result of this, the final molecule that you get, is the resonance hybrid. The hybrid that you get after the actual structure of the molecule after combining or overlapping the different canonical forms. So carbon-carbon single bond should be 154 picometers, carbon-carbon double bond should be 134 picometers, but actually in carbon, the carbon-carbon bond in benzene is 139 picometers and all bonds have equal length. Now, the resonance forms or the canonical forms, they are energetically identical in the case of benzene. Do you see? If you look at the energies of both of these, single bond, single bond, double bond, only the position of the bonds is different. Otherwise, they are both energetically the same. But it has been found that the resonance hybrid is actually lower in energy than any one of these forms. Its energy is lower. And in chemistry, anything that has lower energy has more stability. It is more stable. Right? If it has anything that has to react will have more energy. It has to run, it has to work hard, so it has more energy. But anything that's stable does not require that energy to run around. Therefore, it has lower energy, it's comfortable now. Right? So, it has been found that this resonance hybrid, the actual structure, is energetically lower than the energies of these canonical forms or the hypothetical structures. So energetically, these resonance canonical forms are identical structures, but the hybrid has lower energy. The real structure of benzene is a hybrid of 1 and 2. Right? And what are these 1 and 2? They are called resonance structures, which is the topic of our video. These are called the 1 and 2. The individual hypothetical structures are known as resonance structures or the canonical structures, or they are also known as the contributing structures because both of them are contributing to the actual structure of the molecule. They are hypothetical, they are imaginary. These structures are imaginary and this is the real molecule. So we'll say they are hypothetical and they individually do not represent any real molecule. If you take one of these, although when we are studying organic chemistry and we are studying benzene and its reactions, we do make this structure to explain how the reaction took place. Yet, not one of these actually represents the molecule. So they are hypothetical and individually do not represent any real molecule. They contribute to the actual structure in proportion to their stability. The more, sometimes in this case, in the case of benzene, we had these two canonical forms which have the same stability. Sometimes in more complex molecules, you will have canonical forms, some of which will be more stable and some of which will be less stable. So that canonical form which is more stable will contribute more towards resonance. Because the idea of resonance is to lead to stability. So whichever canonical form is the most stable will be contributing more towards the final structure. So we say that they contribute to the actual structure and in proportion to their stability. Now let us take the second example. Like here we took benzene. Let's take the second example is nitromethane. If you draw the structure of nitromethane, what do we get? We get CH3NO2 is nitromethane. So there's a bond between carbon and nitrogen, and these oxygens we find, one of them has a double bond and the other has a single bond. So the resonance takes place between these two oxygens. The pi electrons of oxygen, that is the second bond of oxygen, that it shifts. Now in this, take a look, that CH3N remains the same in both the molecules. But it is the pi electrons of oxygen, that is the second bond, those electrons are the ones which are resonating between the two oxygens. So these two bonds, they are showing resonance. So what happens in this case, take a look, nitrogen has a double bond with this oxygen, single bond with this oxygen. And in the other canonical form, the upper oxygen has a single bond and the lower oxygen has a double bond. So if we use this curved arrow to show how the electrons may have moved and what the shifting has taken place, like we imagined here that the double bonds, electrons of the double bonds moved between all the carbons of the benzene ring. Here we imagine that this second bond, the pi electrons go to this oxygen, which then acquires a negative charge. At the same time, since this is negatively charged, it lets one lone pair come here and form a double bond. So it gets a double bond here, and then this turns back into this. How? The double bond which is present here now moves to this oxygen, making this negatively charged, while the lone pair of electrons from this oxygen will come down here to make the double bond and get back this structure. So actually, none of these structures is the actual structure of nitromethane. The second bond, that is the second bond between nitrogen and oxygen, is constantly moving between the two oxygens. It is shifting its position, and that is what resonance is. Displacement of electrons. Electrons which are moving and they are vibrating, they are resonating. And that's why it is called resonance. The two NO bonds in the case of nitromethane. The two NO bonds are equal, yes. Another thing, if one was fixed to be a double bond and the other was fixed to be a single bond, again, you would have had a similar situation where the single bond length should be different and the double bond length should be different. But we find that in nitromethane, both the bonds, that is of nitrogen and oxygen, they have equal length and they behave equally, which also indicates towards resonance. So the two NO bonds are equal, that is their length is intermediate between single bond and that of a double bond. So the actual structure is a resonance hybrid between these two. So a similar situation where you imagine both the molecules are overlapped between each other, and this double bond, if you bring it on this, the second bond, this also appears to be a second bond, and this also appears to be a double bond. So both of them are kind of something between a single bond and a double bond. The energy of the actual structure would always be less than the energy of the canonical forms, because hybridization would only occur so that the molecule goes towards stabilization. Any process would not happen unless and until it leads to stability. That is why chemicals react. They are lazy guys. They don't want to work unless and until they have a lower energy, they are more stable, where they don't have to work that hard. So they only work as hard as they have to. So resonance will only take place if the energy of the resonance hybrid is less than the energy of the canonical forms. So we say the energy of the actual structure is less than both the canonical forms. The difference between the most stable form and the resonance hybrid is called resonance stabilization. This is an important term. What is resonance stabilization? When you have different canonical forms having different energies, one of those canonical forms will have the least energy. That canonical form which has the least energy is actually the most stable. And the resonance hybrid will have energy less than this least energy. Only then the hybridization will take place. So the energy of the hybrid is less than the energy of the least stable canonical form. And the difference between these two energies, that is the least possible energy that is possible in the different structures and the actual structure, that difference is known as resonance stabilization. In other words, that is the stabilization that is caused due to resonance. And what is stabilization? Stabilization is lower energy, decrease of energy. So we say this stabilization has been provided by resonance. And therefore it is known as the resonance stabilization energy, the energy which is lost due to resonance. And it is lost so that the substance becomes more stable. An increase in the number of contributing structures. Now we have taken examples where we have only 2 contributing structures. You may have other molecules where the number of contributing structures may be even larger. So the increase in the number of if there are more contributing structures, the greater will be the resonance energy. Because each contributing structure contributes towards the resonance hybrid. And each one, since it is contributing towards the resonance hybrid, it is contributing in decreasing the energy. So an increase in the number of contributing structures increases the resonance energies. What are the rules when you're writing down these resonance structures? The resonance structures, these structures or the canonical forms, they should always have the same positions of nuclei. It means, what is nuclei? Every element, how do you identify an element? Not by its number of electrons, because number of electrons can be lost or gained to form ions. But the identity of an atom is actually the number of protons which is inside the nucleus. So we say every nucleus retains its position. In other words, the atoms of the elements in different canonical forms do not change their positions. They remain where they are. It is only the pi electrons which resonate. So what is the rule? Whenever you're trying to write the resonating structures, you have to take care that the positions of all atoms or all nuclei should remain the same. Then they should have the same number of unpaired electrons. The number of lone pairs of electrons should always be equal. You can't make which means again that the total number of bonds in all of these should remain the same. The total number of bonds should be equal. You may shift the position of a bond. You can't add bonds, you can't remove bonds when you're making resonance structures. The third thing is that the structure which has more number of covalent bonds, that structure, now you will say we cannot change the number of covalent bonds, so how are you saying that? The different structures that you would be making according to the pairs of electrons, the one which seems to be forming more number of single covalent bonds, all atoms except hydrogen should have octet completed. Only hydrogen has a duplet completed because it does not have a second shell. And less separation of opposite charges, that is, the positive and negative, the polarity is less. So when I say less separation of opposite charges, it means that two atoms should not just say that I'm going to be positive and I'm going to be negative. Imagine here, what do we see? That nitrogen has the positive charge, but the negative charge is not fixed on one oxygen. The negative charge is kind of moving, it is delocalized, it is dispersed. So the positive and negative charges, there should be less separation, there should not be really strict separation, and if there is a separation of charges, there should be more dispersal of charge. The charge should be dispersed, as we see here that the negative wobbles between the two oxygen. The negative charge is more dispersed. So there should be a dispersal of charge and there should be a less separation of opposite charges. Then we say that this resonating structure would be more stable. And if a particular resonating structure is more stable, it is going to contribute more towards the resonance hybrid or in the resonance energy. It would have a greater contribution towards the final structure. So the structure which has more number of covalent bonds, all atoms except hydrogen should have their octets completed. There should be a less separation of charges, the positive and negative charge, and there should be a more dispersal of charge. That is, the charge should not be, when we say less separation, it should not be concentrated between two atoms. The charge should be kind of more dispersed. Such a resonance structure would be more stable. So we say, you remember I told you that all resonating structures will not have the same energy. We have taken examples where they have the same energy because they have only two resonating structures. When you have more than two resonating structures, one of them is more stable. Which one would that be? It would usually be the one, when you're writing these structures, of course the rules would be the one structure where there are more number of covalent bonds. All atoms have their octet complete except hydrogen. They have less separation of charges, which means they are not strong positive, strong negative. The positives and negatives are kind of distributed. There is a more dispersal of charges. Such a resonating structure would be more stable. So this was about resonance structures. And with this, I wind up today's video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching and bye-bye for now.